Welcome everybody, I'm Mauro Servienti and today I'm joined by my colleague Sean Farmar. Sean and I are both solution architects at Particular Software, and today we're going to show you how to use NServiceBus to power a web application with real-time request response and publish-subscribe messaging. So let's review the agenda. We'll start talking about what targeted responses are and reconnecting back to where we left in the last episode where Elton showed an implementation of connected back to the client via SignalR. And then we deep dive into all the scale out issues that a simple implementation brings to the table. And then we'll go through some technical solutions that overcome the previously shown issues. And we'll also talk a little bit about the architectural implications of the technical solutions that we are going to show. Last time with Elton, we talked about targeted responses. Targeted responses are basically can be identified as a request-reply pattern. A request-reply pattern is one of the three main patterns when talking about messaging, and we usually talk about request response, request reply, and publish subscribe. There's a really interesting difference between request response and request reply that lies in a really small detail. That is that request response can be compared to two people talking or chatting on the phone, and there's a long chat going on where both of the participants to the chat start talking and responds back with a message to the other one. On the contrary, request reply is a simplified version of the request response pattern where the reply is used just to give an acknowledgement to the original sender of the request in order to say, okay, I got it, or I've done what you requested, and it's just an acknowledgement. We can safely compare a reply to what a mail server sends back when we ask for the delivery receipt. So the server immediately sends back a delivery receipt saying, okay, I was able to talk to the other party server, and so here you go, the receipt. It's a reply, where the response is the email that the recipient of our original message will send back to us to go on chatting with us. So last time with Elton, we see an implementation of the request reply pattern to talk back to a SignalR client. In Elton's sample, he implemented a small chat system where we was able to send a message from a SignalR web client to a backend server, and that server was able to reply back through SignalR, and you will see, Sean will show us in a second how the architecture of that sample was realized. We can generalize the Elton sample talking about a broader request reply pattern where we need to talk to clients or devices such as in the IoT spaces or integrate with the third-party services where we have a change in the transport moving from a message-based architecture using a queuing technology, and at a certain point in the life cycle of the message, we need to move to a different transport. In the case of SignalR, was moving away from the RabbitMQ sample using WebSockets. In other samples can be a totally different transport. One of the generalization that we can do is that the client we need to talk to is not capable to participate in a pub/sub based architecture, and given the nature of the client, we need to be able to translate what an event in a pub/sub based architecture is to something that is understandable by that client. Integration with third-party services can be seen in such a way. We may end up having a legacy application we need to be able to talk to, and that legacy application is not able to talk to a queuing system. So we need to find a way to translate messages to this legacy application in order to allow this legacy application to participate in the long-running conversation that we are going to have.
So I'll introduce the architecture that was proposed in the request reply scenario, and here we're looking at the backend system that has a queuing transport that talks to an HTTP-based front end, which is something like IIS, and then a client like a browser communicating with using a socket technology with SignalR to the client, to the HTTP front end. In this scenario, the client would send a request over sockets to HTTP backend or front end, the backend of the front end, and then that message would be sent to the queue. The backend will pick up the message from the queue and do a bus or reply to the back to the queue, and that will end up on the front end server, and again using SignalR that reply will arrive at the client. I think there's a couple of issues that Mauro is going to talk about now.
Yes, thanks, Sean. One of the interesting issue that this architecture introduced that brings to the table is that, as shown basically last time by Alton, as soon as we start scaling out front ends, for example, we may encounter this interesting scenario. So we scale out the front end using whatever technology you would like to use to scale out, and we may end up having the reply message sent to the wrong front-end instance. So what can happen is that since all the front ends are now behaving in a competing consumer manner using a single input queue, the reply from the back end can be consumed by anyone of the front end. And since the technology that the client is using to stay connected to the front end cluster is not aware of the existence of the cluster, so is directly connected to a specific instance in the cluster. As we are seeing in this sample, it may happen that the instance N, the third one of the front end, is the one picking up the reply, and as soon as this instance tries to go back to the original WebSocket client, that specific client is not there. So there is no way for the instance to reply back to the client. And we may encounter really interesting scenario, because if we rely on the fact that we are able to talk back to the SignalR client, we may end up in a corrupted state or losing some really important information. But there's obviously a solution, isn't it, Sean?
Yeah, I just need to unmute myself. So, yeah. So the solution is the simplest solution would be to create callbacks. Callbacks and now we're talking already in the NServiceBus technology space. So within NServiceBus, if we follow the client calling the socket would end up in the front end. The front end will not only send a message, but delegate a callback on that bus.send. That will end up through the queuing system in the backend system, and when the backend replies, it will do a bus.return and will get back to the correct instance that created to its callback queue, and will then come back to the sockets through the sockets to the client. Obviously, that will work perfectly so long as the instances don't change, because if the reply comes back on a different socket, or if something gets disconnected, then that won't work. So back to you.
Yes.
For issues.
Yes, well, thank you.
No.
So before moving to the next slide, there's an interesting question that I'd like to address immediately. And as usual, I forgot about this. So if you have any question, just use the Q&A panel of GoToWebinar to ask question, and we will address them usually at the end of the webinar. But since the question by Andre Silva is strictly related to what we are seeing right now, I'd like to address it immediately. The question is basically, where is the state of the messages stored? The only thing that we really need to store somewhere is the client ID, the SignalR client ID. That is very important in order to allow the front-end instance to talk back to the correct client. So what we may use in order to store that, the perfect place to store that is the message itself. So we can use the message, we can use headers in the message or a simple property on the message itself to store that information, and what the backend system needs to do is simply add that information back to the message that is going back in this specific scenario to the callback, so that the front end receiving the callback is capable to look through the SignalR hub looking for a specific SignalR client. But as Sean just said, we may encounter some scale-out issues, even with callbacks, because if we expect a reply to go back to exactly a specific instance, what may happen if that instance in the meantime dies? So one of the things that may happen in a scale-out environment is that we scale out in order to be highly available, in order to overcome all the issues related to the fact that one of the instances can die without any advice. And that's why an instance needs to be, as much as it can, stateless. Nothing should be stored at the instance level that is related to the life cycle of the entire cluster. Another issue we can face, and is an issue that can depend on the fact that an instance is just dead, is that the WebSocket connection is lost for whatever reason, and the SignalR client will reconnect back to a different instance. So basically what's happening is that we are still replying back to the callback queue of the front-end instance one, but the client is not there anymore. So we are able to reply back to a specific instance, but due to the nature of WebSocket, that specific instance does not know anymore nothing about the client that is connected, because that client is now connected somewhere else. And we end up basically in the same scenario as before. We may end up losing some important information. There is obviously a solution, otherwise we are not there. So up to you, Sean.
So in this in this kind of scenario, we would introduce something called a backplane. A backplane is like a little broker or a load balancer or like a distributor that sits between the front end's reply mechanism to the front end's send mechanism, which allows us to basically store the state and route messages to all our front ends, if you wish. Which means that in our scenario, if we introduce the backplane, the backplane would register all the instances of the cluster, and will know each and every existing instance of that cluster or the front ends. And then when the bus.reply, when we get a reply back, instead of replying directly to the front end, it will reply to the back end, to the backplane, sorry. And the backplane would then do something like multicasting. It will publish that reply to all the instances, looking to cover, you know, any kind of scenarios where what Mauro just mentioned. So if we have a change of, if our sockets are disconnected and we go from instance 1 to instance 2, then the reply would be on instance 2 and the client will still receive the reply. We also, in the case of the instance 1 failing, instance 2 and instance n, or how many we have, we still get the reply message. This kind of solution is transport agnostic. It doesn't use any kind of transport specific features or anything like that. It is an infrastructure solution, and I would take it as an extremely good solution for many different scenarios in this kind of with this kind of problem. So back to you, Mauro.
Yeah, thanks, Sean. There's a couple of interesting things we can tell about backplanes. That is, one important thing to keep in mind is that obviously a backplane is a single point of failure. So one implementation of a backplane can be done, for example, with a Redis cluster, and we need to talk about clusters. So a backplane as well needs to be scaled out if you want to go down to the path of using a backplane. A backplane is a general solution to a specific problem, and the important bits is that it's transport agnostic. So it can be used regardless of the transport that you are using for the queuing technology. We'll see in a minute that we can use a transport to solve the same solution if the transport supports this architecture. The other important thing is that the diagram does not show it really well, but what happens when using a backplane, depending on how we implement the backplane, what may happen is that all these front-end instances will have their own input queue to receive that is mediated by the backplane itself. So what's happening is that when the reply comes back from the backend system, it will be handled by the backplane. The backplane sits there just to make a copy of the reply that will be available to any of the instances in the front-end cluster. This copy of the reply now sits in the front-end instance 1 queue, instance 2 queue, instance whatever queue. Is there what's the side effect of this? Is that all the instances will handle the reply. They will go back to the SignalR hub, and only one of them will find the client connected. So the message is carrying the state, where the state is the client ID. All the instances will receive the message, and only one of them will successfully handle the message. All the others will just handle the message saying, okay, the client is not connected there, so since I know I can discard this message and I don't care about anything about this message. A backplane, being transport agnostic, is not a portion of NServiceBus. There are many solutions to build a backplane, but there's a thing that is included in NServiceBus that I'd like to show you in order to solve the same issue without introducing a backplane. So one thing that we can have is if we can rely on some specific features of a transporter, we have a feature in NServiceBus called UnitCube per endpoint instance. If you take a look at the diagram, what we have done basically is that we have merged what was the backplane in the previous slide into the queuing system, and we changed its name. So in the sample that we are going to demo in a second, we are using RabbitMQ as a transport. The same features exist in the Azure Service Bus, for example. And what we can create on RabbitMQ is an exchange that has two different behaviors based on where are you looking at the exchange, based on the point of view. So from the backend system point of view, an exchange is a queue. the backend system is sending the reply back to the exchange and is looking at the exchange as a single queue transporting a message. From the front-end cluster, what the front-end cluster can do is basically create an input queue for each front-end instance, and that input queue is going to be bound to the exchange. So what the exchange does for us is that the incoming message from the backend system will be replicated, as in the previous sample using the backplane, to all the front-end instances. And once again, one of the front-end will be the one that successfully ended the message because the socket client is connected to that specific instance. I have a short demo showing this exact behavior. I have two projects in this solution. One project is called Scale-Out Publisher. So it's a standard publisher, can be seen as the backend box in the previous diagram. And I have a scale-out console. The scale-out console is on the other hand, is the one receiving the message. The scale-out publisher is a standard NServiceBus endpoint. So I'm just creating a bus configuration using in-memory as persistent. That is the most unreliable persistent that we provide, but is very handy for demos. Setting the serialization to JSON. It's not really required, it's just a sample. And then defining RabbitMQ as the transport. I'm explicitly disabling callbacks. It's not really required to make the sample work, but it's just to demonstrate that we are not really using callbacks to make this work. And then I'm disabling distributed transactions, so do not have a requirements on my machine to run the DTC. And creating, as usual, as we have already seen in other webinars, the conventions so that a message can be considered an event, a command, or a message. And finally, what I'm doing is simply publishing a standard event, a really simple event containing two properties, a client ID and the message ID, that are basically useless in this sample, but it's just to emulate what Elton shown last time. And on the other hand, I have this scale-out console that has one single difference with the scale-out publisher in its configuration, that is this line. So basically, we can run this console passing a command line argument called instance equal instance number. And if there is a command line argument, what happens is that this endpoint is configured as an endpoint in a scale-out environment that is not going to behave as a competing consumer, but it's going to behave with an exchange in a backplane fashion. So I'm going to show you what happens using one setup and one other setup. And then the message handler in this really, really simple and trivial sample is just doing nothing other than writing something to the console output saying that the message is being received. And I've already prepared all the, oops, sorry about that, there it is, and there we go. So I also have here the RabbitMQ console. At the moment on RabbitMQ, there's no queues at all and no exchanges. Nothing exists. So as soon as the clients will start up, all what is required will be created for us by NServiceBus. And I'll just start up in a competing consumer fashion. And I have 3 clients, so what was called the console, the scale-out console, so the subscriber to the event. I have 3 instances running and 1 publisher. If I go back to the RabbitMQ console, what I can see is that I have 1 queue for the scale-out console and one queue for the scale-out publisher. And there's these satellite queues that are required by NServiceBus to work properly, but it's out of the, it's out of topic right now. So the scale-out publisher queue is the input queue of this console application that is the one sending the message. And even if we have 3 instances running, we have just one single input queue for the scale-out console. And looking at exchanges, we have one single exchange that is used to publish the event by the publisher. And if we click on that exchange is bound to the input queue of the scale-out console. Meaning that if I hit P on this one, what happens is that only one of this console has received nothing, this console has received nothing, this one has received the event. So basically right now we are in the first scenario where just one of the instances received the event that then should be pushed back to SignalR. Now just give me a second that I'll reset the RabbitMQ server so that I can show you what happens as soon as we restart using a different setup. Perfect. So now the RabbitMQ is still completely empty. There's nothing in. Be aware that when resetting RabbitMQ, you are resetting the entire server. So all the configuration of the server will be lost. I'm now starting up the scale-out console, passing in to each instance an instance ID, 1, 2, 3. Using this other batch. And I end up with the same, basically 3 console running and 1 publisher. That here it is. Oops, here it is. But if we look at the RabbitMQ configuration, now we have much more queues. That's very interesting because the scale-out console -1, scale-out console -2, scale-out console -3, and one single publisher, still one single publisher. If we look at the exchanges configuration, we have still all these queues. We still have one single queue for the event, that is the exchange. And if I click on the exchange, what I say is that all the 3 input queues of the scaled out console are bound to the same, exactly to the same exchange, meaning that they will receive, all of them will receive a copy of the event as soon as, of the message, in general, I'm using pub/sub in this case, but it's just a message, of the message as soon as the publisher publishes it. So if I go back to my client and I hit P once again, all the consoles have now received a copy of the message. As you can see, as I hope you can see from the green message that just appeared on each instance of the scale-out console. So basically we have solved the exact same issue that the backplane is meant to solve using something that is built in the transport, and that NServiceBus is capable to gain advantages using this unique queue per endpoint instance feature. There's obviously some interesting consideration that I expect the architect that lives in Sean will immediately do.
Okay, can you hear me now? Yeah, I think the screen refresh was a bit slow. I'm not sure, so apologize for that. Mauro?
Oh yes. Sorry about the slowness of this streaming. Yes, sorry.
Yeah. No worries. So, so the main point, I guess, to take from that is the not losing the single responsibility principle in the whole thing. The fact that we publish an event to multiple subscribers is a technical use of publish, because if we actually do some business logic on our front ends, so instance 1, 2, and 3 will all go ahead and proceed to do some kind of business logic on the front end, then we have a serious problem on our hands, because let's say that each of those front ends is going to do some, process a credit card transaction or push an order to back to create an order on another system or something like that. We are going to have multiple events, multiple processes running at the same time. We're going to duplicate all our events, and this is a serious caveat. Yeah, so this is meant not to be used as in this scenario. And generally speaking, a front-end server should not be doing any kind of business logic whatsoever. It should be the view in the MVC that is the V. It is not supposed to do any kind of business logic apart from being a channel between the front end or the client and the back end. So this is a serious consideration to be very aware of, and be very careful not making this little mistake. Mauro?
Yes, very good. Thank you for all these comments, Sean, that from the architectural perspective, and I totally agree that it's very important to clearly separate responsibilities when using these techniques. Otherwise, we may encounter issues that we're running the business logic multiple times, and it's not really what we want.
Mm-hmm. Okay, I just want to take this opportunity while you're all here to tell you about our NSBCon. It's coming up really quick. It's a 4-day conference that includes an NServiceBus crash course, a Saga masterclass workshop, and we have great presentations from Ted Nuhr, Rob Eisenberg, Udi Dahan, and many more. And it's in Dallas, in Texas, the 1st to the 4th of December. And for more details, you can go to particular.net/NSBCon 2015. And there's I think there's still like discount tickets going on there. So we hope to see you there. Mauro?
Yes, so thank you very much for attending. We have a long list of questions in the Q&A panel, so I'll start reading the question and we handle them while going. So there's a question from Davok Bradley that is for request reply, why wouldn't you use a synchronous call to a web service from the client with the web service handling the service bus? For request, so it's obvious that the sample is in that respect is a bit awkward. So it's very handy to have a front end offloading immediately the client request to a back-end server in a couple of scenarios where we have a really high load on the front end, and the front end just behaves like a stupid mean to translate a request from one transport WebSocket in this sample to something else, the queue. Or another interesting scenario is where we have a long-running process that maybe is triggered by some messages, and the client is connected and wants to have feedback on that long-running process. So one thing that we may happen to have is that we have a process handling an order, the client is connected, and we want to have some sort of real-time update on the UI in order to, whenever an event is published on the back end related to the specific process, that event should update the UI. So that's that's a good reason to use this specific approach. And there are many others, obviously. But it's obvious that if we just think about this specific sample, using a synchronous call will easily solve the problem. Okay, we already talked about the fact that the backplane. Yep, sorry, Ed. Sorry, Sean, go ahead.
No, go on. I think Andre Silva's questions were answered before, correct me if I'm wrong, but the front end with SignalR, do we keep a correlation ID? Yes, we pass it in the message to between the front and the back end for the hub to then go and reply to the correct client. And is the backplane is centralized, and again the single point of failure was mentioned by Mauro before, so I'm hoping that those were answered. So if again, for failure to mitigate failures, we need to do some kind of hardware clustering infrastructure type of a solution in order to mitigate that. Aditya asked, are there any retry mechanism when Backplane attempts to send a reply back to the instance in the cluster? So technically, yes, it could be done with messaging. Basically every instance would have a queue, and we do a bus.send to that queue effectively. And if there is a failure there, that is a technical failure, there'll be retries until successful. If that fails, the outgoing message is going to sit in the outbound queue of the backplane, and it will eventually end up in your dead letter queue or something like that if the instance is gone forever. I hope that answers the question. And Andre asked about the backplane being a part of the NServiceBus platform, and it is not, as Mauro said. So
yes, there's a
turn, Mauro.
Yeah. There's a question from Goethe De Pickere, sorry about the pronunciation, and when I mentioned that it's transport dependent on Azure, yes, it's only available with the Azure Service Bus. So the Azure Storage Queues has no knowledge at all of what an exchange is. I sincerely do not know what happens if we try to use the unique queue per endpoint instance when using the Azure table storage queues as a transport, but I'll get in touch with Eve Go11 and ask about this specific and get back to you via email so I can be more precise. There's another question from Andre about in-memory persistance. It means that when you reboot, you lost all the information. Basically, yes. So in-memory persistance, what we need to persist, depending on what the endpoint is doing, we may need to persist timeouts that are used by the retry engine to decide that a message should be retried because failed the last time within 5 seconds. That information is stored in the persistence engine. We may need to store subscriptions in order to allow a publisher know that there's subscribers interested in some events, and we may need to store sagas. We may need to store some others information as well, but not on this specific topic. So yes, using in-memory persistence is an unreliable persistence. It's mainly taught for demos, and it's taught also for endpoints that do not really care about persisting in a persistent manner their information. In the sample we just did, we can think about that the front ends are not really interested in persisting anything because since the connection with the SignalR client is volatile itself and it's not persistent, there is no need at all to persist anything. They are just subscribing to an event published by the backend, and at the backend, there is the need to persist that subscription in a much more reliable manner. So at the backend level, in a production environment, it's not really suggested to use in-memory persistence. There's a question from John that is, do you recommend a queue like RabbitMQ as shown here? That's a very complex question to answer in a webinar. So I'd say that it really depends on the use case and the scenario you're going to implement. But Rabbit being a broker, it's an obvious single point of failure. So the broker itself needs to be scaled out. RabbitMQ has, let's say, 3 main ways that ranges from clustering to federation to shovel to achieve what can be considered a cluster. Only using the real clustering infrastructure, you will end up having what can be really considered a cluster. But in all 3 scenarios, we end up having a scaled out broker. It's really complex to correctly configure RabbitMQ to be really reliable when used as a cluster. So it really depends on the use case. So I'm not going to say.
Well, I would like to add to that,
Yes,
Mauro, that
yes.
I would use RabbitMQ only in a scenario where you actually need cross-platform integration, where you want Java and to talk to your system. So there's 2 downfalls here. One is that you're using a broker to begin with, which is again, it's a single point of failure, and to talk to kind of make it clear, when this broker goes down, your whole system goes down. It's not like this server over there just went dead. Oh, that's a shame. We'll bring it up and everything is going to be all right. It's like everything is down. Each and every endpoint in your system is now down. If something, if you have a cluster and the connection to the cluster just went down, yeah? So it's not the servers are up, everything's fine, but the connection to the cluster is gone, then your single point of failure becomes a system-wide failure. So it's important to kind of realize that and be ready for that. In addition to that, you're using an HTTP-based proxy to communicate to that broker, yeah? So you're getting another compounding problem with reliability that I think you should consider very heavily before going and using that. So definitely, I hope that answers the question. And I think, the more you distribute and the more you make it reliable, the better off you are. If you're already developing a complex system that's using messaging, then do yourself a favor and make it as reliable as you can. Martinez asked about, will this work with MSMQ? So I assume that you're asking about Mauro's demo. It will, but then you'll need to use a backplane. You won't be able to use, in the demo we used, Mauro used Rabbit's exchange capabilities, and that doesn't exist in other transports. So if you want to use MSMQ or other transports that don't support it, then you would have to use the backplane solution.
There's an interesting question from Evan pointing out, so why if RabbitMQ is not as reliable as we expect, why are you using to show you in this specific scenario? Well, to answer this question and another one, the unique queue per endpoint instance is transport agnostic on transports that support this feature, such as the Azure Service Bus and the SQL transport as well. So there's a question from Yossi and one from Morten regarding this. And so we can replace the transport moving from RabbitMQ to the Azure Service Bus and the SQL Server transport, obtaining the exact same behavior. My original intention was sincerely to run this demo on the Azure Service Bus, but due to connectivity issues and due to the slowness, as you may have noticed, of the connection, was not really a good idea to break the demo because of the connectivity issues with the Azure Service Bus. And it was a good way to, as a segue from where we left with Elton, that used ZeroMQ and RabbitMQ as clients, as queuing technology, sorry.
Okay, so Andre has asked if we support, NServiceBus supports message correlation. So yes, it's part. It's it's a part of the framework and the platform. If you look into the message headers, you'll see all our correlation IDs running around. So we get who's the sender, and what was the intent, and what SAG ID if there's a SAG, and so on. So I hope that answers the question. Mauro, do you want to take the next one?
Yes, there's a, let me just scroll through. Okay, where you can get the sample code, you will receive, you will receive an email after the webinar end with a link to the webinar recording and a link to the sample code that you can download. And please, if you have any question related to what we talk about today, just ping us at support@particular.net, and we can help you in moving forward with the sample or solving specific business case related to your environment. There's a couple of questions related to NServiceBus v6 that will be released soon. I'm not allowed, unfortunately, to say when. It is soon. And there's a question related to, are we going to support IBM MQ natively? We used to have a transport, but we decided to, due to some limitation of the .NET client, to stop supporting it. We constantly monitor the transport ecosystem in order to see if there's new transports that are valuable and there's value in supporting them. It's important to understand that supporting a transport is much more effort than simply writing the code to talk to the transport. So that's an important issue to keep in mind. The same thing is related to the Windows Server Service Bus. That it is the on-premise version of the Azure Service Bus, and actually is in some sort of a limbo by Microsoft itself, and we are trying to understand where Microsoft is driving the Windows Server Service Bus in order to decide if there's value in supporting that transport as well. I'd say that we are running out of time, so we'll go through all the unanswered questions, if any, and get back directly to you via email. So don't worry that all the questions will be answered. And so that's all we have for time for today. I'd like to, on behalf of Sean Farmar, this is Mauro Servienti saying goodbye for now, and see you on the next particular live webinar. Thank you very much for attending.